Good afternoon, everyone. Welcome to our ESA's Roundtable System Seminar today. It's my great pleasure to introduce our distinguished speaker, that is Professor Jennifer Dunn from Northwestern University. So Jennifer holds a Curtis appointment, I think, in mechanical engineering, but her primary appointment is an associate professor of chemical and biological engineering at Northwestern University in Evanston, Illinois. So Jennifer is also the Associate Director of Northwestern Argonne Institute of Science and Engineering and Associate Director of Northwestern Center for Engineering, Sustainability, and Resilience. So her research focuses on emerging technologies, energy and environmental impacts, and the potential to influence greenhouse gas and air pollution, water consumption, and energy consumption at the economy-wide level. She also looked into a variety of technologies, including biofuels and bioproducts, automotive lithium-ion batteries, waste plastic recycling and utilization, advanced manufacturing, and fuels and chemicals from natural gas liquid. She pretty much used tools from techno-economic analysis, life cycle assessment, and material flow analysis. And she also applied machine learning techniques to gain insights into land use and land use change. So Jennifer holds a PhD in chemical engineering from University of Michigan. And she also been, prior to joining Northwestern, she has been very active in Argonne National Lab in the DOE space. She led the biofuels analysis group in Argonne National Lab and also managed Argonne's relationship with Department of Energy's Bioenergy Technology Office. So I had very much a lot of pleasure, collaborating with Jennifer when I was working at Northwestern. Gee, just time flies. It's almost like 10 years so far, right? Yeah. So thank you very much, Jennifer, for joining us today. The presentation of her seminar today is guided post and guardrails analysis to guide energy and materials transitions. So Jennifer, it's all yours, please.
Thank you. Well, it's really a pleasure to spend time with you all today. I really love that you have a systems engineering kind of concentration. That's really, really wonderful because I'm, of course, of the opinion that systems level thinking is really what we need to solve the many challenges that we're facing as a society. So today in my talk, I'm going to focus on 3 case studies of how our group has used analysis to kind of guide some thinking around some of the transitions that we are experiencing as a society. But before I get into those case studies, I wanted to just give a little bit of an overview of my research group at Northwestern and the areas that we work in. So when thinking about how to sort of bucket the different work that we do, these are the 5 buckets that I came up with. So these are the 5 areas that we focus on. And even though we can sort of devise or think about these individual buckets, of course, when you get into systems level work, all of these really touch on each other. So you can't think about the bioeconomy without thinking about water. And you can't think about the circular economy and manufacturing without thinking about plastics. So these things all intertie with each other, which is both a challenge and also a lot of fun as an analyst to think about these interconnections and how to best model them out in ways that help us think about how we should guide our technology transitions. These are the members of my group. So I have 6 postdocs and 3 PhD students and 1 master's student in the group. And I'm very fortunate to work with these really, really wonderful people. And so the work that I present today is work that they have developed, working with me and with other collaborators, both at Northwestern and outside of Northwestern. So even though this is a group that I'm sure has a really solid grounding in energy systems and overall systems, I thought I would still spend a little bit of time to set the stage for the analysis that we've been doing. And really that comes down to thinking about how the energy landscape continues to change, because energy is really the constant thread through all of these systems. None of them work without energy. So one of the biggest transitions that we're undergoing is our thinking about transportation. And of course, you're all familiar with the saying, electrify everything. And so this is the push that we're hearing, especially in the light duty sector. And so there are lots of ways to think about it. Many people carrying out analyses in this area that it can help us think about how this transition might occur. So just as an example, I chose this figure from the Carbon Tracker group because they put on one graph a number of different scenarios that could kind of guide thinking about how this might take place. So on the left-hand axis, we're looking at year-on-year oil demand growth in million barrels per day. And that's the axis where you read the dashed blue lines from this, the projections in oil demand growth from OPEC and from the International Energy Agency, one of their scenarios. And so we see over time, we expect that to decline. You'll notice that that steep decline there is actually behind us. I don't think we quite managed that, but nonetheless, both of these scenarios show an eventual significant decrease in oil demand growth. At the same time, some of that will be displaced by the use of EVs to provide the energy we need for transportation. So again, depending on which report you look at, you're going to see different projections. This figure summarizes or includes projections from 2 oil companies and 2 entities that look at the energy space and make projections. So perhaps unsurprisingly, it's the 2 oil companies that have the lowest expectations for displacement of oil by electric vehicle operation. But there's one analysis group that really has quite an aggressive scenario. But when you put all of these together, we could be looking at peak oil demand in this decade. That's a possibility. And so the question then becomes, as analysts, well, what else are we doing besides EVs to help us meet our energy needs? Because they can't do it all, and they can't for transportation, and we're not going to be able to meet our GHG reduction targets through EVs alone. So if we're going to lean on other technologies in addition to EVs, how do those things interact? How can they be complementary to each other? And what are the implications then for water consumption, for air pollution, all the different environmental effects that we as humans experience? So these are questions that we can get at through analysis. Another big transition is the drive to just make plastics entirely circular. And so there are groups that put out position pieces like this, the one in Science this past fall, that really emphasize the need to do this, which I don't think anyone disagrees with. And that would be achieved through reducing virgin plastic production and consumption. So a lot less use of crude oil and natural gas to make plastics. And then in the meantime, we need to design our plastics to be recyclable. Those design decisions could mean using different materials, using different manufacturing processes, different designs that could influence the durability of plastic products that we use. And then in turn, we're going to need to come at it from the other side. So designing waste collection systems, designing recycling processes to manage some of, for example, the heterogeneous plastic products that we have. But all of these decisions and approaches, they have systems level effects that we need to consider and think about, and just try to avoid doing things that have negative consequences, but perhaps more from an optimistic perspective, try to design these systems so we can achieve maximum environmental benefits that really get us towards our goals. And so to me, that's the role of systems analysts. We are here to help provide guideposts and guardrails. To me, the guardrails come first. We want to sort of do these big scenario analyses that help us see what's possible and where don't we want to go, like what do we need to stay away from? And so that helps us set our path forward. I'll just make a quick side note that when I was looking at Google Images to try and find a guardrail post or guardrail image that didn't have a copyright associated with it, the best one has this bird. And so I'm just going to say the symbolism of the bird is that we're using our guardrails to help protect us, keep our quality of life good, and also make sure that we're still having our healthy ecosystems. So the guideposts, once we have our guardrails there, we need guideposts for our different types of technology to help us understand what technical targets we need to hit. So to help us stay within our guardrails for these individual technologies. So that might be around a recycling technology. How much tolerance does it need to have for contaminants, or for any particular biofuel? What do we need to be achieving in terms of water efficiency of processes that make biofuels? Those are the types of technical guideposts that we as analysts can help set. I'm going to focus a little bit more on the guardrails in today's talk, but the guideposts is really no less important of an outcome of systems analysis. So I'll get started with the first case study. So this is around this transition that we're seeing in our fuels, in our transportation space. So transportation, of course, represents about 28% of our greenhouse gas emissions, big push to electrify. And that's primarily focused on the light duty fleet. But meanwhile, we have our heavy duty vehicles, our trucking, also our airplanes, and our large ocean going vessels, for example, the marine sector. These are very difficult to electrify and accordingly difficult to decarbonize. And you have to kind of wonder, couldn't we put, we need liquid fuels. Well, couldn't we sort of emphasize a use for biofuels to be in these hard to decarbonize sectors? So we really wanted to understand the complementary roles of electrification and biofuels in transportation overall, and think about how we might best direct our biofuels resources. Now, in doing these analyses, we assumed that there would be widespread electrification in the light duty sector. And we used for our electrification of light duty a scenario produced by the National Renewable Energy Laboratory that had in the light duty sector 88% of cars and 81% of trucks electrified by 2050 in the light duty sector alone. And that electrification came in the form of mostly purely electric vehicles, so not hybrids, not plug-in hybrids, but pure electric vehicles. So that was our kind of baseline. We're going to electrify the light duty fleet. Now, what can we do with our hard to decarbonize transportation types so that we can improve upon our decarbonization outcomes? So Fenchi mentioned that I have a lot of sort of history in the biofuel space. I led the biofuels analysis group at Argonne for a number of years. And my conclusions out of that body of work is that biofuels are low carbon fuels. They have a lot to offer in the realm of decarbonization, and they should not be overlooked. There are so many different kinds of biofuels that can be produced. So they can definitely be produced and tailored to meet the needs of these hard to decarbonize sectors. So we can make many different types of fuels via many different types of pathways, thermochemical, biochemical, and hybrid. And these different technologies are at different readiness levels. So some of them, they could be ready, in the very near term. Some will take much longer to develop. And so we need to kind of plan for that and be aware that we need to have this pipeline of technologies that we're going to bring on board. So we set out with these pathways and also many others to think about how these different pathways could then contribute to fuels, could contribute to decarbonization. But of course, you can't do that unless you have the biomass. And the Department of Energy in 2016 released a billion ton report, basically looking at how can we get to 1 billion tons of biomass by 2050. And in this report, on the left-hand side, there's a business as usual scenario that basically says, look, we're just going to kind of carry on how we are now. We've got some corn ethanol, we've got some soybean biodiesel, we're chugging along. Versus a scenario in which biomass has much more value and can be used for any number of end uses in a broader bioeconomy. So this was termed the 1 billion ton scenario. When you compare the left and the right figures, you'll notice that most of these types of biomass get a boost, whereas wastes tend to stay pretty constant because we don't necessarily want to be increasing the availability of waste. But the big contributor here to that actually over 1 billion tons is energy crops. And those are miscanthus, switchgrass, and short rotation woody crops, which are poplar and willow. And so these are the really kind of, I would call the workhorse of the bioeconomy, is these energy crops. Okay, so we have these projections, we're going to use those, but now the question is, how are we going to put that biomass to good use? And there are just, of course, an infinite number of ways you could do that, and you could use any number of algorithms to try and determine that. But we set out to establish some guardrails through three different scenarios. We're trying to see what our possibilities are here. So in our first scenario, we said we're not going to have any favorites for our application of biomass. We're going to assume that aviation, marine, and heavy-duty trucking all have equal blending of biofuels into their base fuel supply. And this is going to increase incrementally at an even pace across all three sectors. So, scenario 2, I call the low-hanging fruit scenario. So I'm sure you've all seen press releases from airlines like United and others. They are already using biofuels in some of their flights. Aviation recognizes they have limited options for decarbonization, so biofuels are the way to go at the moment. When I was working primarily in biofuels, it was really refreshing to hang out with aviation folks because they were very gung-ho on biofuels. So we know that aviation is an early adopter. We're going to prioritize them for this biomass resource that they can use towards biofuels. Also in this scenario, we assumed a pretty aggressive electrification outlook for heavy-duty vehicles, and that was again based on the National Renewable Energy Lab study. In the third scenario, we take the biomass resources, spread them pretty evenly between aviation and heavy-duty trucking as our first priorities, and then the marine sector sort of gets the leftovers. But we were kind of careful and strategic in thinking about leftovers for marine. We focused on things like renewable natural gas for manure and landfill gas that could be used in marine applications. So I have the briefest methodology slide ever here. You've heard about our baseline or our benchmark, how we identified our biomass resource, how we defined our scenarios. Our reference case was the Annual Energy Outlook 2020 scenario. So we basically took those scenarios where we have fuel consumption by type and by year. We assigned life cycle metrics, life cycle greenhouse gas emissions, water consumption, air pollution emissions that are derived from the greenhouse gases, regulated emissions and energy use and technologies, or the GREET model that's developed out of Argonne, where I still hold a joint appointment. And we paired those impacts with our progression of fuel use over time in a derivative model of GREET called bioeconomy age. So to show you some of the results from this analysis, I'll begin with our approximations, our projections of how the share of energy use in these different sectors would vary with our scenarios. So we're treating the light duty sector the same across our three scenarios. Aggressive electrification. Electrification is providing like around half of energy use in the light duty sector in 2050, with gasoline at about 32%. Now, if we zoom in on scenario 2 for aviation, right? This is where we say, okay, aviation is an early adopter. We can get to about half of the aviation energy demand for fuels. We can meet about half of that with biofuels in that scenario. Otherwise, in most other scenarios, we're hitting around 30% of energy demand being met with biofuels. The kind of exception here is in the heavy duty sectors for scenario 2, we assumed the large penetration of electricity. So that's at about 15% of the heavy duty demand in that scenario. Marine tends to hover around like 18 to 20% of energy met with biofuels. So this is the shares of energy that we're looking at across these scenarios. Now, if we translate that into our environmental metrics, this is what we arrive at. I've described the different scenarios to you, but for each scenario, we can actually look at two different cases for the achievable cost of biomass. So this derives directly from the Billion Ton study. That study looked at these two different price points. And the simple laws of economics, a very simple case is that when you can get more for biomass, you're going to make more. So in the $60 per dry ton case, we have just more biomass available to apply towards decarbonization. So if we look at this top left panel, our blue line here is our AEO reference case. So we see a little decline in GHG emissions because we're making energy efficiency gains, and we're seeing some increased electrification even in the baseline scenario. But then emissions do rise and go up. Now, if we move to the yellow line, this yellow line represents what happens if we just do electrification, if we don't take advantage of our biomass resource in the US. So we're definitely achieving GHG reductions around 28% reduction when we do that alone. But when we add in our biomass resource to help decarbonize these hard to decarbonize sectors, we achieve additional energy benefits, about 11%. And this, you get more when you go for your more biomass resource through assuming a higher price point for biomass. One interesting result here is that given the thought that we put into these scenarios and kind of the care we took in building out the annual progression of biofuels, we don't need to worry about if we're using biomass in the right way. No matter how you slice and dice it, it comes out looking pretty good. If we had to pick a winner, it's scenario one at the $60 per dry ton price point that achieves the lowest amount of GHG emissions. But when we think about applying this to policy, a policymaker could take kind of a sigh of relief. No matter how its biomass is deployed to these hydrocarbonized sectors, we're doing well with GHG emissions. If we turn our attention to water consumption, we start to see a little bit different picture. We have the lowest water consumption in our baseline case, and every other case besides that has higher water consumption. And that really comes down to two factors. One is that electricity tends to be more water intensive than fossil fuels. Fossil fuels are just really water efficient, and it's hard to do better than that. And so this may involve a trade-off, even though we know we need to worry about water because water scarcity will increase over time with climate change. From the biofuel side, just some biofuels routes are very water inefficient. And so this to me is a guidepost. So it's a guardrail that we need to worry about water if we're going to go for this bioeconomy approach. But the guideposts come in when we say, okay, technology developers need to know about this and they need to prioritize water efficiency as biofuel production processes are produced or developed. And of course, we also need to look towards feedstocks that require zero irrigation. And that actually was assumed in the billion-ton study for the energy grasses. It was assumed that they would be grown in regions where they did not require irrigation. PM 2.5 emissions, this is a success story. I used to work at the Environmental Protection Agency, and PM 2.5 emissions drops are really great from a cost benefit of policy angle because human life is really protected when PM 2.5 emissions are lowered, and human life is of course precious and then therefore has a very high monetary value in a policy context. So good stuff on reducing PM 2.5 emissions, and we need to kind of know that and point that out as we talk about the advantages of using biofuels for decarbonization. And fossil fuel emissions results as lower right-hand panel, this tracks with the GHGs, which makes sense because most of these emissions just derive from burning fossil fuels. Okay, so looking good, but let's think about some other effects, like effects on refineries. It goes without saying refineries will experience a lower demand when the bioeconomy and increased electrification take off. So even without biofuels, so here the solid lines in this figure represent the demand for fuel type from refineries in our baseline scenario. So we've got gasoline and we've got diesel here, and also jet and residual fuel oil that's used in the marine sector. When we go towards high electrification, we see the demand for gasoline drop. So again, this is nothing to do with biofuels, just that aggressive electrification scenario. We see it drop even more when we take into account biofuels in terms of total demand for refinery products. So here we see diesel decreasing compared to our reference case. And for jets, we see of course, a pronounced decrease here in scenario 2 because we're prioritizing biofuels for aviation. So overall, a drop in demand for refinery products. So that could entail perhaps refineries taking on the processing of biofuels or the blending of biofuels into existing petroleum products. So that's an important transition to keep in mind. One thing that's also kind of interesting is that today, of course, we have this gasoline diesel imbalance where our refineries are producing much more gasoline than diesel. And kind of, no matter where you fall in these scenarios, that balance among refinery products is much more evenly split, which actually is a positive. Okay, so the elephant or the 500-pound gorilla or whatever large animal you want to pick in the room when you talk about biofuels is land use. And so, of course, we looked at this metric. When we think about these scenarios and the different price points for biomass at the $40 per dry ton price point, we're actually we see a decrease initially and then an increase here, but we kind of get back to our baseline point. So it's not going to be too bad, but when we look at the $60 per ton dry ton price point, we see a significant increase in demand for land. So it's around 30 million hectares. But when you look at these results, and the next important question is, what kind of land are we talking about? Is it primary cropland? Are we switching out food for fuel? It's possible to grow a lot of biomass on marginal land. So if we look at where is this land coming from, in the $40 per dry ton scenario, a little less interesting than the big push for biomass scenario. So these gray bars here reflect switchgrass, which can be grown really on marginal land. Sorry, the orange bars are the switchgrass that can be grown on marginal land. And the gray bars here are the miscanthus bars. So again, marginal land. Now, what does marginal land mean? Typically, marginal land is a little bit lower quality in terms of soil quality. Typically, you'll have lower yields of conventional crops, so farmers don't want to plant on this land. The estimate of how much marginal land we have in the US really varies by data source, so much so that I was trying to understand this a few years ago. So back in 2017, I did a study looking at this. And basically, there's so many different definitions of marginal land. There are multiple data sources you could use to try and understand marginal land resources, that it's quite a range. So I came up with a range of 59 to 107 million hectares of marginal land. So depending on your scenario here, you could be looking at using between 2 and 23% of that marginal land. But the key point is here, we don't necessarily need to encroach on existing agricultural land or onto the natural lands that we all worry about, because they are very important for maintaining ecosystem services, biodiversity, and also we just like them, and we want to keep them for just many reasons. So when people really talk about land use, I really think it's important to make this point, because this is a very sensitive issue in the biofuels and the bioeconomy arena. So much so that I've spent a lot of time trying to understand what we really know about our land base, because my concern has been that we're going to take biofuels off the table over concerns about land that aren't necessarily justified or could be addressed through policy design or incentives for farmers, things like that. So in the past 10 years, I've spent a fair amount of time on this for a chemical engineer. But luckily I have fantastic collaborators, and we work together on these questions. So what this figure shows is a range of different data sources and their estimates of these key land types: croplands, grasslands, wetlands, and woodlands. And knowing nothing about these different data sources, if you kind of just take a step back and look at these results, the cropland area comes out, regardless of data source, to be pretty similar. Right, so we got a good handle on croplands because we care about croplands. These are all data sources from the US Department of Agriculture. It's their job to make sure we know how we're using our cropland, to understand our food that we're getting, and do we have any food insecurity issues or anything like that. So that's kind of keeping an eye on that, right? So that's the main motivation for their data collection. But you'll notice within this cropland class, there is some variation among this hay and harvested grass, for example. And that sort of feeds into a larger problem with our understanding of grasslands, which is much more varied. And this is where we start to get into trouble, because some of our remote sensing based data sources tell us we have a lot of grasslands, and that conflicts with some of our other data sources. So if you're starting from a point where you think we have a lot of grasslands, then we have a lot to lose. And so it's important to understand these different data sources when you're reading about people's estimates of land use change. And woodlands also, I feel like, we should have kind of a pretty good handle on how much forest we have, but it turns out that our estimates actually vary to some extent. So I'm hoping this paper will be out soon. We just got our reviewer comments back. They're very manageable. And my hope is that this paper can make a contribution to some of this confusion around the state of land in the US. But that said, I spent so much time kind of trying to figure this out that I got a little frustrated, and I wanted to do something about it besides just consuming existing data sets. So when I came to Northwestern, I met a person who does image analysis with artificial intelligence. And historically, he's worked on medical imaging, but I convinced him to work with me on trying to apply machine learning techniques to high resolution aerial imagery to maybe more sort of automate the process of understanding our natural lands. So we've worked primarily so far on wetlands. We have a really nice data set in Illinois on where our wetlands are. I didn't know this existed. I've been an Illinois resident almost my entire life. We do a great job with our wetlands. I did not know. But we basically use these data sets to develop testing and training data sets for our algorithm. We developed a new neural network algorithm. We called it WetSegNet. And basically that algorithm helps us kind of find wetlands in these images. So just to give you a sense, we have about a 99% accuracy with this method. The red line is the ground truth data from the Illinois Natural History Survey, and the blue line is what our algorithm says. So we're able to do this at a 1 meter resolution, and the existing remote sensing data sets are at a 30 meter resolution. So we can catch really ecologically important small wetlands with this. We of course hope to continue working on this. Being good at finding wetlands in Illinois is great, but we need to be able to do this in all states, and also for grasslands, which, as I mentioned, are really important. So kind of conclusions around this whole question of biofuels contributing to decarbonization. In my opinion, we need biofuels, but also biofuels and electrification can't do it alone. We need many technologies, including fuel cells, for example. There are a lot of concerns around biofuels, in particular with water and land. And I think that's where we need our guideposts to set us water efficiency targets, for example, and to help us to develop techniques to help us monitor how we're using our land base with a greater accuracy that can help guide policy. Okay, so I'm going to shift to another case study, but it still pertains to transportation because electrification is one of our main strategies that we're leaning on. And back in 2012 is when I started working on doing life cycle assessments of lithium-ion batteries. And to be honest, I didn't know much about them. And I didn't know much about their supply chains. So as I'm reading and doing things, I'm reading things like there are concerns around the effects of mining for these metals on the communities that mine them. And I kind of had to set that aside for a while. Just kind of, I was sort of wondering about it. But to give you a sense of this, we get about half of our cobalt, which is a really important component of lithium-ion batteries. We get about half of that from the Democratic Republic of the Congo. And within that country, there's a particular region that produces a lot of that. And in that region, there are about 100,000 to 150,000 small scale or independent miners who mine this cobalt, effectively with their hands. And it was bothering me for a long time that we couldn't quantify those types of social effects because there's child labor and all this. We couldn't quantify that with the same rigor that we can quantify our environmental effects. So again, I kind of had to set it aside because this is not my area of expertise at all as a chemical engineer. But when I came to Northwestern, I met an anthropologist, and she develops cross-culturally validated scales to measure water insecurity. And these are quantitative, they make sense to me as an engineer. And so I wanted to explore with her how we might use the construct of social life cycle assessment to help us quantify the social effects of these new technologies. And of course, I'm interested in social LCA overall, but my initial interest has been around lithium-ion batteries and their supply chain. So, this challenge has been known for a long time, and it's in the popular media. It doesn't just affect our car batteries, our lithium-ion batteries for cars. It affects the batteries in our phones. I have a battery in my vacuum cleaner. My dad has a hedge trimmer that's electric. Like, it's just everywhere, right? So this is a problem that goes beyond cars, but because I focus on transportation, that's where my emphasis has been. And it's not like no one's doing anything about it. There are efforts to try and mitigate this from the private sector, the public sector. But I feel like in the policy discussion, there is precedent, especially in the transportation space, for using environmental life cycle assessment to guide policy development here in the US, in the European Union, Japan, Colombia, like many countries are using environmental LCA. And so I see an opportunity because of this familiarity to use social life cycle assessment as a tool towards a more comprehensive effects assessment than we can get from environmental LCA. So this is where I started working with Sarah Young to try and explore this question. Sarah Young is the anthropologist at Northwestern. So the purpose of social LCA is makes sense from what its name is, to promote the improvement of our social conditions and overall socioeconomic performance of a product. And the way that social LCA is set up, it's kind of in this framework around stakeholders. And there are different categories of stakeholders you see here. The metrics are different than we see in environmental LCA, of course, and they include things like safe and healthy living conditions, local employments, working hours, and fair salary. And these are things that you can't just slap a sensor on them like you can on a power plant stack and measure. These require interactions with people. So I'm assuming that many of you are familiar with life cycle assessment, and that may be a poor assumption. But for both environmental and social life cycle assessment, the framework, the steps you take are the same, but there are, of course, differences. But when you begin, you set up your goal and your scope, and that is pretty much the same. You could have an identical goal and scope for an ELCA and an SLCA, and indeed that's what I'd like to see in the future to be much more common. And I do see some examples of it, but we're still in the early days, in my opinion. Phase 2 is where, to me, it gets more interesting, right? You need data, and we all know that in modeling, the quality of your model results really depend on the quality of the data that you put in. And this is where I feel like we have a really significant gap. This is where I was trying to work to identify ways that we could build improvements. Phase 3 is where you do your impact assessment. You use the data you collect in phase 2 to quantify indicators. So in environmental LCA, global warming potential is a pretty common one, right? But in SLCA, as I mentioned, it might be something more like fair salary. And then in the interpretation phase, this is when you take what you've learned and you apply it to either how you're going to design your product if you're a company, or how you're going to design a policy, or potentially if you're a consumer, which product you're going to buy. So this is where you would act basically on your results. So what we set out to do, again, was really to focus on that phase 2. What could we learn about the situation in cobalt mining to inform kind of an overall strategy to improving data collection in SLCA phase 2? So we set about with this methodology to kind of learn more about the situation, select a method, and then we did work with a colleague from a community college in Minnesota who is from this region. He traveled there and carried out our exploratory field research. And then after that, he sort of contextualized that research based on this social life cycle assessment stakeholder categories. And based on that experience, we developed recommendations. We didn't have sufficient resources or time to do a full LCA. That, as we learned, is really time intensive. And the salient sort of social effects that Gabriel, our colleague, observed are those that we've read about. Basically, cobalt mining is very disruptive to life in these communities. The landscape itself, just the urban landscape, if you can imagine walking down any street in Ithaca and having a mine dug right in front of you, that's the reality in these regions. Child labor, you can see in the bottom right, is definitely occurring. And the role of women in this enterprise is primarily, often women are not allowed in mines, but they take the ore that's collected and then they wash it, and they have just incredibly high levels of cobalt exposure. So really, none of this is taken into account when we talk about we need to electrify. These things are not talked about at the same level as the environmental benefits we can get from electrification. So what can we do to improve our metrics? I just want to make a quick point that there are some data available that can be used in social LCA, but they tend to be at the country level. And we just know, just from your own life experience in any given country, no matter which country you're from, regions of that country that are struggling and regions that are doing really well. I'm from Chicago. There are regions that are just fantastic, and there are regions that are struggling. So national level data really, to me, is not enough. It's not sufficient to base decisions upon. And I have just a small example of that, changing the emphasis for a moment from Democratic Republic of the Congo to South Africa. South Africa is where iridium is mined, and I've been thinking also about some fuel cell work. So iridium is salient to that. And if you look at the national stats for South Africa, 48% of South Africans have a secondary education, but in the region where most mining for iridium occurs, that's only 31%. So just a concrete example of how local data is needed compared to national data. And when we think about how we might generate these data for these different indicators within SLCA, they have different costs, right? So doing surveys and talking to people like we did one-on-one or in focus groups, that's very time intensive. It's not realistic to expect that we can generate the types of data we need based on that type of interaction. Maybe we go in, we as a community would do a deeper analysis or investigation of a certain area based on hotspot analysis, but overall that strategy won't work. There's an opportunity potentially to use public documents like land-related court claims to investigate indicators like delocalization. So people losing land to those who want to set up mines, like basically on their land. People have been kicked off of their property for that in this region. And then safe and healthy living conditions is a general indicator. One of those is access to food. And so because of my previous work using remote sensing to understand agricultural land, I see an opportunity to use those type of data to really get into understanding food insecurity. In the work that Gabriel did, he talked to people who said they used to be able to buy food basically like within a 10-minute walk, and they were even at times having to cross an international boundary to get the food that they needed. So food security is definitely decreases in food security is an outcome of cobalt mining that you might not anticipate. But my colleague Sarah Young, as I mentioned, she develops cross-culturally validated scales. She tends to focus on water insecurity, but there are parallel scales for food insecurity, also women's empowerment. These types of scales that the social science community has developed, I think they're powerful tools. I'd like to see them used in SLCA, and I hope to work with Sarah to bring that into reality. So our recommendations based on this case study are summarized on this slide. I've talked a lot about the need for better data at finer scales, but also it's just super apparent to me that engineers and scientists, we are the ones who sort of devised ELCA, environmental LCA, and accordingly kind of applied that mindset to SLCA, but we need social scientists involved with us to do this right and to do this well. And I think that we can't solely focus on environmental effects. Of course, environmental and social effects are tied, but there are many social effects that just aren't captured in what ELCA can tell us. And I think that we need to elevate the urgency of discussion around social effects for many of the technologies we're leaning on to help us address climate change. Okay. My last case study is really shifting gears because I'm going to talk about an entirely different analysis technique, material flows analysis. And what I want to highlight in this case study is how you can use material flow analysis to establish guideposts and guardrails. So with this analysis, we were focusing on polyurethane. We were looking for opportunities to increase circularity in the polyurethane system and also for opportunities to increase bio-based content. So you might ask, why polyurethanes? Polyurethanes are super interesting. They're the 6th most dominant polymer in the US, and there's a lot of work at Northwestern actually on making polyurethanes more recyclable. So we chose that as a focus of a project we proposed to DOE, which was funded. And so we've been working on this for about 1.5 years. But basically we're trying to identify, again, ways to increase the renewable content and recyclability of polyurethanes. And so the analysis portion of this project, we worked together and put and assembled this material flow analysis of polyurethane in the United States. And I'm sure many of you are familiar with the Sankey diagrams out of Lawrence Livermore National Lab on energy flows in the US. I mean, to me, these charts are so useful. They are very hard to assemble, but once they are assembled, they just tell a wonderful story for opportunities and they help you understand how changes you could make could either make this better or make it worse. In the case of polyurethanes, when we look at this figure, we see 2 things right away. All polyurethanes come from fossil fuels, and there is incredibly little circularity in the system. It is a highly linear system. So this chart is organized starting from our fossil fuel feedstocks and going all the way through end of life. It highlights the precursor chemicals are made that are dominated by isocyanates and polyols. There are also some adhesives, which are things like flame retardants. And then we have the polyurethane material itself. So the 2 dominant categories here are rigid foams and flexible foams. You'll note that we do import. We took into account imports and exports. So these come into our system mostly when we're getting to our final product. We tend to mostly import polyurethanes as opposed to importing precursors to polyurethane products. So we took into account our imports and our exports in this work. We then get to the end of life. So you'll see that the building and construction sector is a dominant user of polyurethanes as well as transportation. And we have also a lot, makes sense, right? You have foam in your furniture and in your mattresses. So that category is here as well. So then we get to end of life. And what's notable, right, is we've got a lot of building and construction material for polyurethane, but when we get to end of life, this flow really shrinks because these materials have a long lifetime. On the other hand, we have more of an end-of-life flow from things like our carpet underlayments. That has a much shorter lifetime. So, it's really important in this type of work to dig into that end-of-life phase. So we looked a lot for information about how long these different products live, and we built a log normal distribution based on that information. And so I'm zooming in here on these bar charts. So for polyurethane in building and construction, we have the building and construction continue to increase its use of polyurethanes over time. And this is the amount that was produced in 2016, the year of our study. There's not that much making its way into the waste collection, as we mentioned, because of the long lifetime. Transportation also took a while to start using polyurethanes, but we're seeing more of waste from this sector coming out of the system in 2016 than in the building sector. So hence the thicker flow for that line. But this long longevity of some of these polyurethanes present a challenge for polyurethane recycling because back in the 70s, 80s, 90s, we used substances that are now banned. So if you take a mechanical recycling process and try and get polyurethanes back out of that, chances are you're going to have stuff in there that we should not be using anymore. Yet mechanical recycling is really the dominant approach to achieving like this level of circularity, which is still small, but it's the only circularity we have going on here. And that's really driven actually by post-industrial waste, just a tiny bit of post-consumer waste coming in here. So what are our opportunities to increase the circularity of the system? And one thing that's you can just take away really quickly from this diagram is that we throw away more flexible foam than we produce. So let's focus on that flexible foam. That's a guidepost that we can really take to heart. And the good news is that there's technology out there like Holysys that can actually accomplish that. It's actually a commercial scale in Austria. But when we think about what we need to do here quickly, let's get that technology here. Let's scale it up. Let's use it in the US. Let's think about how we can collect this. We need to build our collection systems to make that a reality. And then if we think about renewable content for biomass, if we were able to make all of our isocyanates from bio-based materials, we would then result in having a 19 to 77% of bio-based content in those polyurethane products. On the polyol side, that range would be 7 to 65%. So we might want to prioritize our isocyanates for bio-based compounds, but certainly, again, a lot of room for improvement considering there's basically no bio-based content to date. So I just wanted to provide kind of those high-level takeaways from that MFA. There's, of course, a lot of detail that underlays that type of analysis. But I think overall, you could imagine doing the type of analysis I presented in the first case study with this type of MFA diagram, where you link those flows with carbon intensity, water intensity, sort of come away with where we can make the most impact. So I think overall MFA is a really powerful tool that I intend to continue using. So I just have a really brief conclusion, and that I think we can all agree that systems level perspectives are really important in solving these challenges that we face, whether it's trying to redesign our material system or trying to redesign our fuel system. We need to take that holistic full supply chain perspective. These are the acknowledgements that I'd like to offer. And at this point, I'd be happy to take any questions.
Very good. Well, great. Thank you so much, Jennifer. Wonderful presentation. Thank you. Now I think the floor is open for questions and discussions. Anyone ask anything?
This is always
maybe I could just, I do have a few questions, if it's okay. So the first question, of course, I know you have been working a lot on biofuel space, right? We collaborate in this space. Recently, there's a very strong voice on hydrogen. And I guess you heard about it, right? I mean, people are talking about hydrogen for everything. Oh, yeah. Hydrogen for aviation, hydrogen for marine transportation, hydrogen even for heavy duty vehicles and light duty vehicles. So how would you see the competition between hydrogen and biofuels in the long run?
I mean, I subscribe to the old Obama era phrase of the all of the above. So for hydrogen, I just think that some of the biofuels technology is nearer term. And for hydrogen, there's this issue of right now we make it mostly from natural gas. So it really needs to be natural gas drive hydrogen with carbon capture. And so that presents a problem or a challenge for economics, I guess. But at the same time, I have a different project more in the fossil fuel space where I'm really trying to say that I think we need to take our natural gas resources that we have and sort of put them towards that use to build the infrastructure for hydrogen, to sort of de-risk the technology, because we're asking people to put a lot of faith in something that we don't have a lot of right now. So to me, there's an opportunity, also for biomass, right? You could gas by biomass and get H2, but let's try and de-risk that technology while we build towards electrolysis. And using our green electrons for that purpose. So I definitely see a role for hydrogen. And at Argonne, I just am aware there's a lot of work around how can we decrease the energy consumption associated with sort of compressing hydrogen and moving hydrogen around. So that's one of the key challenges for hydrogen. But I think that smart people are working on those problems. They have their guideposts in place. They know where they're trying to get in terms of their energy efficiency targets. And so I think that's coming online. But again, I think we should take every chance we can to de-risk and build out infrastructure for the hydrogen economy. So we can have a hydrogen economy, bioeconomy, we can have all these economies. I don't know what we call the whole thing, but we need some name for like an inclusive economy.
Yeah, sure, that's nice to be inclusive. I don't know if anyone want to ask the next
I have a question.
Okay, Ahmed, please.
Thank you. Hello, this is Ahmed. I have a question regarding to the biomass or renewable energy and in terms of actual policy. So you worked for the government for some time, I understand from your presentation. Like there are some states, I know of Virginia, state of Pennsylvania. I'm sure there are other states also. They're like, if people wanted to buy electricity, there is an open market for buying electricity and you can pick your own supplier. For example, like if your household can consume more than 5 kilowatt per hour rate, you can actually pick your own supplier instead of relying on whoever owned the infrastructure or the distribution. So in this sense, in this open market, people can choose renewable energy by company and they pay that company, and the company will put that amount of electricity demand on the network for in a general sense, and eventually you will get your electricity, but you're paying for that. So in terms of policy, why no universities or local governments or federal government, they actually opt in electricity consumption for their own facilities that is a part of renewable energy or biomass or anything. Basically, you create a demand void that has to be filled by this. It will create a new market. People will enter the market because now there's a supply for that. And from a policy term, at least can kickstart some kind of a fluctuation between the norm that we have here, and maybe there is a potential for people to get into the market and make it more competitive. Do you see any like initiative government-wise or organization-wise to opt in using policy?
Oh, I have to admit that the electric grid is something that it's not really in my area of expertise. So I don't feel like I can really answer your question.
I understand. Thank you.
Yeah, liquid fuels. I tend to focus on liquid fuels, like the renewable fuel standard is primarily, well, it is all about liquids, with one exception, renewable natural gas to basically do combined heat and power to fuel EVs. But that's it. That's kind of where I feel comfortable. So I apologize.
Great. All right. Thank you. Any other question for Professor Dunn? Richard, you want to chip in? You are muted.
Yeah. You can hear me now, yeah?
Yeah, now we can hear you. Yeah.
I had curious about direct burning of biomass. For example, the wood pellets being sent to Europe for electrical generation. I've read a couple of papers that said that's not even close to being carbon neutral, and that it's actually worse than coal in some cases. Yeah, I wondered if you had any comment on that, and also
okay, go ahead.
And I also wondered about the status of this lignocellulosic system for producing liquid fuels. Is that actually becoming viable, or is that still a pipe dream where using switchgrass and that sort of stuff, is that actually producing fuel, or is it still in the future as it seems to have always been in the future?
I'm not sure if it's quite the 30 years like fusion. But so I'll address your first question around wood pellets for energy, right? So this is one of those situations where I feel as though sometimes analysts undertake assumptions that maybe bend an analysis a certain way, and they aren't fully transparent about that. So what happens with the wood pellet analysis often really depends on what you assume is your counterfactual scenario. So back in 2015, I remember I was about to leave work and I got a call from my DOE sponsor who wanted me to help her understand a report that had come out of a UK environmental group around this very question. And I actually use that report in the LCA class that I teach, because they showed in many cases that using wood chips for bioenergy was worse than coal. And it came down to the fact that they assumed that if you did not harvest those wood chips, you would instead let an old growth forest grow, or like that you would somehow change that into a prairie. And I think the thing that those types of scenarios miss is that these forests are already being commercially managed, and they're very unlikely to revert back to anything like the rainforest that you see out in the Pacific Northwest. Like it's so. In the work that I've done around this, we collaborated with experts in forestry who taught me a lot about forest management and how land is managed in parcels. And basically it's kind of like a carbon bank. Like you take some, but you grow some. And so on a landscape level, you want to try and be somewhat carbon neutral. So I definitely think there are cases where it could be worse than coal. But when I sort of get like frankly annoyed about is when people say, oh, well, otherwise we'd have an old growth forest there. And then they just put the graph, and then people take that graph and they go in front of a policymaker like, this is terrible. And so this is where I kind of get on my high horse about policymakers, because how are you to know that that counterfactual scenario is what's driving that results? And the second question, now that I have to get off my high horse, was about lignocellulosics. So yes, when you look around the US today, you do not see fields and fields of switchgrass on marginal land. And so that is definitely a futuristic scenario, but what we do have is agricultural residue. So there are some parts of the US where corn yield is so high that you have to take off some of the residue if you want to get your tractor through. And we've learned a lot about in instances where you wouldn't have to take off the residue, but you want to still manage your farm sustainably, so you're maintaining or increasing soil carbon levels. We've learned a lot about that. And so there's a lot of things we can do conservation strategy wise to enable sustainable use of agricultural residue. And to me, that's feedstock number one. So if we think about that de-risking, you start with that residue, you build up your system, and then once you've convinced all these farmers to grow switchgrass at your $40 per dry ton and $60 per dry ton price point, you know, that whole infrastructure of like managing, because it's not easy to manage this biomass, like grind it up and get it ready for use. I mean, just because of my time at Argonne, I know there are people like at Idaho National Lab, there's an entire user facility built around how do we process this biomass to get it ready for the reactor throat. So that's, you know, still an area of research, but I feel like we start with corn stover, which is happening, but not anywhere at the scale that was envisioned in the renewable fuel standard. Like we were supposed to be like totally gung-ho by 2022 with 36 billion gallons, and that has not happened, right? But I still think it's a worthy goal because I really understand the potential for emission reduction. So I hope we keep at it. I hope that when my grandkids are like, oh, that's a field of switchgrass, you know, it wasn't here in 2020. Yeah.
Great, thank you. Any other question? Maybe I could ask one very quick question if it's okay. I think we have 1 minute left. The social LCA study you did on this battery system is very interesting. I don't see that many studies going on. And I guess, you know, as you mentioned, the main challenge is really the data, right? Sometimes we don't get the data, and even you get the data, we may not be able to kind of validate its error bound to some extent, because some of these sort of have a significant variations. And I'll probably also argue that these numbers also change with time, right? Basically, if you look at the social impacts, right? Social impact 10 years ago is different from social impact now, even for the same system. So I'm wondering, you know, have you ever taken into account this time dependent as a dynamic system, a dynamic impacts of LCA, no matter social, environmental impacts? into the study? And what's your perspective on this kind of, perspective, something like that, or maybe dynamic, perspective in these systems analysis?
I mean, the only way I've been able to incorporate it is through snapshots in time. So I myself haven't really built a dynamic model. I built a model and then put in data from, let's say, like 2015, 2020, and then some futuristic scenario. And it's just so hard, like, especially on the social side, I struggle with knowing, like, how would we do that? So I don't know, my hope, I was talking with Jillian earlier, like, you really hope for like people, I don't know, we make an argument in our paper that hopefully we publish soon, like who these people should be that should fund these data collection efforts. So people need to fund this. And it's like not as exciting as like, okay, I'm going to do this massive analysis and I'm going to like, but so to me, it's a case of selling to funding agencies the need to support this data collection, which I'm starting to see a little bit of a shift there. So I think there's some hope, which is why I wanted to get this done and get this out to try and make the case that this is needed. And it's needed, and we need, as you know, convergence is a hot topic in NSF. So, this is truly a convergent area of research. As an engineer, I understand the technical system. I understand the materials that are needed. And then my colleague, the anthropologist, like, she knows how to measure social impact. So we need to work together. And that's why I get kind of excited about the convergent research things. I feel like it's finally stuck, like, and it's valued. So that's why I have hope in that department.
Yeah, that's great. Thank you very much. I guess we are kind of close to the end. If there's no more question, please join me to thank Professor Dunn again for the wonderful presentation today and for visiting us virtually. Thank you very much, everyone, for joining us. And thank you, Jennifer, again, for a great talk.
Absolutely. Thank you.